Welcome to this brief but important explanation of a critical phenomenon in structural engineering, buckling. You've probably heard of structures collapsing unexpectedly, and in many cases, buckling is the hidden culprit. So, what exactly is buckling? Why does it happen, and how do engineers prevent it? Over the next few minutes, we'll explore these questions to uncover the dangers of buckling and its role in structural failures. What is buckling? Buckling occurs when a structural element, like a column or beam, suddenly bends or twists under compressive stress. Imagine holding a long, thin ruler upright and pressing down gently from the top. At first, it resists the force, but at some point, it bends to the side. This is buckling. In real structures, this can be extremely dangerous. Columns in buildings or bridges are especially vulnerable to buckling when they are subjected to too much weight or force. Why does buckling lead to collapse? Buckling is dangerous because it often happens without warning. When a structure buckles, the load it was carrying can no longer be supported. For example, in a skyscraper, if a column buckles, the entire weight of the building above that point may no longer have the proper support, leading to a rapid and catastrophic collapse. This is why buckling is one of the key failure mechanisms that engineers must consider in their designs, especially for tall buildings and slender structures. Critical load, the tipping point. So, what determines whether or not a structure will buckle? Engineers calculate something called the critical load, which is the maximum load a column or beam can handle before buckling. This depends on several factors, like the material, the length and shape of the element, and how it's supported at both ends. Once the load goes beyond this critical point, even a tiny increase in force can cause sudden failure. That's why understanding critical load is essential for designing structures that can withstand compressive forces. Preventing buckling in structural design. To prevent buckling, engineers reinforce structures by adding bracing, using stronger materials, or making columns thicker to resist compressive forces. Sometimes, reducing the length of the columns or providing better support at the base can also minimize the risk. By understanding the causes and effects of buckling, engineers can create safer structures that won't fail under unexpected loads. Conclusion. In summary, buckling is a silent but severe threat in structural engineering. When a structure buckles under compressive stress, it loses its ability to support loads, leading to potential collapse. By carefully calculating the critical load and designing to prevent buckling, engineers ensure that buildings, bridges, and other structures remain safe and stable, even under heavy loads. Thanks for listening, and remember, structural safety is all about understanding and preventing failures like buckling. Welcome to Blueprint to Reality. Today, we're exploring groundbreaking innovations in earthquake dampers, specifically base isolators and tuned mass dampers, and how they help protect buildings from seismic vibrations. The challenge of earthquakes. Earthquakes are unpredictable and can cause severe damage to buildings by shaking them from their foundations. Traditional structures transfer these forces directly from the ground to the building, leading to cracks, collapses, and structural failures. But innovations like base isolators and tuned mass dampers are revolutionizing how we build to withstand seismic events. Base isolators. Let's start with base isolators. These devices are installed between a building's foundation and its structure, acting as a buffer during an earthquake. Instead of letting the building move with the ground, base isolators allow the foundation to shift independently from the rest of the structure. This reduces the amount of force transferred to the building, dramatically lowering the risk of damage. Base isolators typically consist of layers of rubber and steel with a flexible core. When seismic waves hit, the isolators absorb and spread out the energy, allowing the building above to sway gently without absorbing the full impact. Tuned mass dampers. Now let's talk about tuned mass dampers, another powerful innovation. These are massive weights, usually installed at the top of a building, that move in opposition to seismic vibrations. When an earthquake shakes the building, the damper swings in the opposite direction, effectively canceling out much of the motion. Tuned mass dampers are carefully calibrated, or tuned, to match the building's natural frequency. This tuning allows them to absorb and dissipate the energy from seismic vibrations, preventing the building from swaying too much and reducing structural stress. How they work together. Together, base isolators and tuned mass dampers create a powerful defense against earthquakes. Base isolators protect the building from ground motion, while tuned mass dampers reduce vibrations in the upper structure, making the building safer and more resilient. Innovations like these are changing the way we design buildings in earthquake-prone areas, saving lives and protecting property. Thanks for watching Blueprint to Reality. If you're fascinated by how engineering solves real-world challenges, don't forget to like, subscribe, and hit the bell for more exciting insights. Introduction. Hey everyone, welcome back to Blueprint to Reality. In today's video, we're diving into a topic that's more relevant than ever: how to design buildings that can withstand extreme heat conditions. As climate change intensifies, many regions are experiencing record-breaking temperatures. This poses a serious challenge for buildings, especially in areas prone to heat waves. But don't worry, we have some smart structural solutions that can help make buildings more resilient to rising temperatures. Thermal mass, the power of heat absorption. The first solution to consider is thermal mass. But what exactly is it? Thermal mass refers to a material's ability to absorb and store heat. In buildings designed for hot climates, materials like concrete, brick, or stone can be used to regulate indoor temperatures. By absorbing heat during the day and releasing it slowly at night, thermal mass can reduce temperature fluctuations. This helps keep interiors cooler during the hottest parts of the day without relying heavily on air conditioning, which saves energy and reduces the building's carbon footprint. Shading strategies. Passive cooling. Next up, let's talk about shading. Strategic shading is a low-cost, passive cooling technique that can make a world of difference in extreme heat. Roof overhangs, awnings, and exterior shading devices like louvers and pergolas can block direct sunlight from hitting the building's windows and walls. By keeping the sun's rays off the building, shading reduces the amount of heat entering the structure. It's simple, yet highly effective. Combining shading with reflective or light-colored materials further minimizes heat absorption, keeping the structure cool from the outside in. Ventilation and airflow. Letting the building breathe. Proper ventilation is another key factor when designing for extreme heat. Buildings in hot climates should allow for natural airflow to circulate cool air through the space and expel hot air. Architects often use techniques like cross-ventilation, where windows on opposite walls are aligned to allow fresh air to flow through. Stack ventilation, which uses height differences to encourage hot air to rise and escape, can also be used to keep interiors cool. Innovative materials. Reflective and heat-resistant. Finally, let's explore some innovative materials. Reflective roof coatings and paints can bounce sunlight away from the building, reducing heat buildup. Insulating materials like aerogels provide superior protection against heat transfer, keeping interiors comfortable. These materials not only protect against extreme heat, but also improve the building's energy efficiency, making them a smart choice for future-proofing structures. Thanks for watching. These are just a few structural solutions that can help buildings withstand extreme heat. If you found this helpful, don't forget to like, subscribe, and share this video. Stay cool, and I'll see you next time on Blueprint to Reality. Welcome to Blueprint to Reality, where we explore groundbreaking ideas in civil engineering and architecture. Today, we're diving into a fascinating sustainable building technique that's gaining momentum around the world: rammed earth structures. Introduction to rammed earth. Rammed earth construction isn't new. It's an ancient building method that's been around for thousands of years. Used in structures from the Great Wall of China to Moroccan Casbahs, rammed earth is a technique that involves compacting layers of damp earth between forms. The result? Strong, thermally efficient, and environmentally friendly walls. Advantages of rammed earth. So, why are we seeing a resurgence of rammed earth today? First off, sustainability. As we face the challenges of climate change, the construction industry is looking for greener alternatives. Rammed earth uses natural, locally sourced materials, reducing the carbon footprint. Unlike concrete or steel, it doesn't require high-energy production processes. Secondly, its thermal properties are a major benefit. Rammed earth walls provide excellent insulation, helping to regulate indoor temperatures naturally. This means reduced energy consumption for heating and cooling. modern applications, and innovations. In recent years, architects and engineers have started to reimagine how rammed earth can fit into modern design. From luxury homes to eco-friendly resorts, rammed earth structures are finding their place in contemporary architecture. Advanced construction techniques and new materials, like stabilizers, are improving the strength and durability of these buildings while maintaining their natural aesthetic. Designers are also experimenting with various pigments and textures, creating visually striking structures that blend seamlessly with their surroundings. Rammed earth is a perfect blend of ancient wisdom and modern innovation, offering a sustainable, durable, and beautiful building solution. As we move forward in the age of eco-conscious design, this technique may play a key role in reshaping how we think about construction. Thanks for tuning in to Blueprint to Reality. If you're passionate about sustainable design and cutting-edge architecture, don't forget to subscribe and hit the notification bell for more insightful videos. Welcome to Blueprint to Reality. Today, we're talking about some of the most infamous cases of engineering gone wrong. From bridges to skyscrapers, engineering failures can have catastrophic consequences. We'll explore 7 famous structural disasters where mistakes in design, construction, or maintenance led to tragedy. These incidents remind us why precision, attention to detail, and adherence to safety standards are crucial in the world of civil engineering. 1. Tacoma Narrows Bridge, USA, 1940. Let's start with the infamous Tacoma Narrows Bridge, nicknamed Galloping Gertie. Built in Washington state, this suspension bridge dramatically collapsed just months after it opened in 1940. Wind-induced vibrations caused the bridge to sway uncontrollably, as captured in now-famous footage. The design overlooked the effects of wind on such a flexible structure. This disaster revolutionized how engineers approach aerodynamics in bridge design, highlighting the importance of accounting for natural forces. 2. Hyatt Regency Walkway Collapse, USA, 1981. Next is the Hyatt Regency Walkway collapse in Kansas City, Missouri, in 1981. During a hotel event, 2 suspended walkways gave way, falling onto a crowded lobby below. This collapse killed 114 people and remains one of the deadliest structural failures in U.S. history. The cause? A change in the original design for the walkway's support rods, which couldn't bear the load. This disaster emphasized the dangers of modifying structural designs without thorough re-evaluation. 3. Ronan Point Tower, UK, 1968. The collapse of Ronan Point, a residential tower in London, occurred just 2 months after it was completed. In 1968, a gas explosion on the 18th floor caused one corner of the building to collapse like a stack of dominoes. The failure exposed the fragility of precast concrete panel construction and poor connections between structural components. This disaster led to stricter regulations on high-rise buildings in the UK and better safety standards for gas installations. 4. Sampom Department Store, South Korea, 1995. In 1995, the Sampom Department Store in Seoul collapsed without warning, killing over 500 people. The building's failure was caused by illegal modifications to the original structure, including the removal of support columns and overloading of the rooftop. The disaster was a wake-up call about the dangers of ignoring engineering principles in favor of profit, stressing the importance of strict adherence to structural integrity. 5. Florida International University Bridge Collapse, USA, 2018. In 2018, the pedestrian bridge at Florida International University collapsed just days after its main span was installed, killing 6 people. The collapse occurred due to design flaws in the bridge's tensioning system, which created cracks that went unaddressed. This tragic failure underscored the importance of early detection of structural problems and following protocols during construction. 6. Rana Plaza Factory Collapse, Bangladesh, 2013. The Rana Plaza factory collapse in Bangladesh is one of the deadliest structural failures in history, killing over 1,100 workers in 2013. The building, which housed multiple garment factories, was poorly constructed with substandard materials and unauthorized floors. The collapse revealed the extreme dangers of cutting costs at the expense of safety and led to worldwide scrutiny of building regulations in developing countries. 7. Savar Building Collapse, India, 2017. The Savar building collapse in India, also known as the Lotus Business Park fire, involved the collapse of an under-construction building due to poor materials and design. This incident highlighted the need for quality control and proper oversight, particularly in fast-growing urban areas where construction standards may be compromised. Each of these disasters demonstrates what can happen when engineering goes wrong, whether through design flaws, cost-cutting, or poor execution. But they've also paved the way for better practices, stricter regulations, and new technologies. Thanks for watching Blueprint to Reality. Be sure to like, subscribe, and hit the notification bell for more content on engineering, design, and the lessons we can learn from past failures. Stay safe, and we'll see you in the next video. Welcome to Blueprint to Reality. Today, we're diving into one of the most impressive feats of engineering, suspension bridges. These towering structures seem to defy gravity, effortlessly hanging between 2 points. But what's the secret behind their strength? The basics of suspension bridges. At first glance, suspension bridges are marvels of simplicity, but don't be fooled. The science keeping them standing is anything but basic. A suspension bridge consists of 3 key parts: the deck, cables, and towers. The deck is the part of the bridge you drive or walk on, but it's not just resting on solid ground. Instead, it's suspended by cables, massive steel ropes that connect the deck to the towering vertical structures on either end, called the towers. These towers hold most of the weight. How suspension works. Now, here's where the physics comes in. Those steel cables are the backbone of the suspension system. When a load like cars, trucks, or even people moves across the bridge, it creates downward force on the deck. The cables take that force and spread it across the entire span of the bridge. They transfer the load to the towers, which then transfer it down into the ground, or foundations, deep beneath the surface. Think of the bridge as a giant hammock. The cables are like the ropes of the hammock, and the deck is like the fabric. The weight on the bridge causes tension in the cables, but the towers act as anchors, keeping everything in balance. Stability and flexibility. An important feature of suspension bridges is that they're designed to be both strong and flexible. In fact, flexibility is crucial. Winds, temperature changes, and even earthquakes can cause the bridge to move slightly. That movement helps it absorb stress instead of breaking. Engineers calculate how much sway a bridge can handle to ensure it stays standing, even in harsh conditions. The cables are made from thousands of smaller steel wires twisted together, allowing them to carry incredible weight and remain flexible enough to handle shifting forces. So the next time you drive over a suspension bridge, take a moment to appreciate the science at work. It's not just concrete and steel, it's an intricate dance of tension, weight distribution, and flexibility. That's the magic that keeps these bridges standing tall and strong. Thanks for tuning in to Blueprint to Reality, and we'll see you next time. Welcome back to Blueprint to Reality. Today, we're diving into a critical topic for modern infrastructure: how engineers make bridges earthquake-resistant. Bridges are vital lifelines, connecting communities and supporting transportation networks. But when earthquakes strike, the forces can be immense, threatening their stability. So how do engineers design bridges to withstand seismic activity? Let's explore the key techniques that keep these structures standing tall during earthquakes. Understanding seismic forces. First, let's quickly understand what happens during an earthquake. Earthquakes generate lateral forces, side-to-side movements, that can shake a structure violently. Bridges are particularly vulnerable because they span long distances and need to support heavy loads, like vehicles and trains. During an earthquake, the ground beneath a bridge can move unpredictably, creating forces that can cause columns to crack, joints to fail, or even lead to complete collapse if not designed properly. Flexibility through base isolation. One of the most effective techniques engineers use to protect bridges is base isolation. This involves placing flexible bearings or isolators between the bridge structure and its foundation. These isolators act like shock absorbers, allowing the bridge to move independently of the ground during an earthquake. By isolating the movement, the bridge can sway with the seismic waves without absorbing the full force of the ground shaking, greatly reducing the risk of damage. Dampers to reduce vibrations. Another key tool in earthquake-resistant design is the use of dampers. Think of dampers as a way to slow down the vibrations caused by seismic forces. Engineers often install tuned mass dampers or viscous dampers within bridge structures to absorb and dissipate energy. These devices can reduce the amplitude of vibrations, minimizing the impact on the bridge's key components like its deck and supports. Dampers essentially help calm the shaking, protecting the bridge from excessive stress. Reinforced pillars and foundations. The next critical aspect of earthquake-resistant design is reinforced pillars and foundations. Engineers use reinforced concrete and steel to strengthen the columns and piers that support bridges. This reinforcement helps resist the intense shear and bending forces caused by earthquakes. In some cases, engineers also use deep foundations or piles that extend far below the surface to reach stable soil or bedrock, ensuring the bridge remains stable even when the ground above it shakes. Expansion joints. Lastly, bridges are equipped with expansion joints. These are gaps or flexible connections that allow different parts of the bridge to move independently during seismic activity. By providing space for controlled movement, expansion joints prevent parts of the bridge from colliding with each other or cracking under stress. They help ensure the bridge can flex without breaking. By using base isolators, dampers, reinforced pillars, deep foundations, and expansion joints, engineers create bridges that can resist the devastating effects of earthquakes. The goal isn't to make bridges completely unmovable, it's to allow them to flex and absorb seismic forces without collapsing. Thanks for watching Blueprint to Reality. If you enjoyed this breakdown of earthquake-resistant bridges, be sure to like, subscribe, and hit the notification bell for more insights into the world of civil engineering and design. Stay safe, and see you in the next video. Welcome back to Blueprint to Reality. Today, we're taking a closer look at one of the most critical parts of any skyscraper, its foundation. How do these massive buildings, some reaching over 1,000 feet, stay upright without sinking or toppling over? The secret is in the engineering of the foundations. Let's break it down. The basics of foundations. Foundations are essential for distributing the enormous weight of a skyscraper to the ground beneath. But it's not just about supporting weight. Foundations also help skyscrapers resist forces from wind, earthquakes, and even the shifting of the earth itself. There are two primary types of foundations used for skyscrapers: shallow foundations and deep foundations. For small buildings, shallow foundations are usually enough. But skyscrapers? They need something much more robust. Deep foundations explained. Skyscrapers rely on deep foundations, which go far below the surface to find solid ground or bedrock. The most common types are piles and caissons. Let's start with piles. Piles are long, slender columns made of concrete, steel, or even wood that are driven deep into the earth. These piles either reach bedrock or are driven into dense layers of soil that can support the building's weight. The goal? To transfer the load from the skyscraper down to a stronger, more stable layer of earth. Next, we have caissons. Imagine caissons as giant, concrete pillars, almost like enormous, buried columns that reach bedrock. Workers excavate deep shafts, fill them with concrete, and voila, you've got a super strong foundation. Challenges of building foundations. But it's not always easy. In cities like New York and Chicago, where skyscrapers are everywhere, engineers have to deal with unpredictable soil, water tables, and nearby structures. Sometimes, they use a technique called friction piles, where the friction between the soil and the sides of the piles helps support the weight of the building. Another key challenge is settlement. Settlement happens when the soil under the foundation compacts over time. If one side settles more than the other, the building could tilt or crack. Engineers have to design foundations to minimize this uneven settlement. How foundations resist external forces. Now, skyscrapers aren't just sitting on the ground. They're battling natural forces like wind and earthquakes. This is where the foundation really shines. Wind. The foundation anchors the entire structure, preventing it from swaying too much. Engineers even build in flexibility, allowing the skyscraper to move slightly without causing damage. In earthquake-prone areas, the foundation often has to absorb seismic energy. Engineers use flexible materials and base isolators in the foundation to cushion the impact of an earthquake, reducing the stress on the building itself. Real-world examples. Some of the world's tallest skyscrapers have incredible foundations. Take the Burj Khalifa in Dubai. It stands over 2,700 feet tall and has a foundation that extends over 160 feet into the ground, made up of reinforced concrete piles. Then there's the Shanghai Tower, which uses both piles and caissons to deal with the soft soil and seismic risks of the region. Its foundation is built to withstand high winds and potential earthquakes. So, how do foundations support skyscrapers? By reaching deep into the earth, anchoring the building to solid ground, and resisting the natural forces that could bring it down. Without these marvels of engineering, the towering skylines of cities around the world wouldn't be possible. Thanks for watching Blueprint to Reality. If you enjoyed learning about the engineering secrets of skyscraper foundations, don't forget to like and subscribe. See you in the next video. Welcome back to Blueprint to Reality, where we explore the world of civil engineering and how it shapes our modern lives. Today, we're tackling a significant challenge faced by engineers worldwide: how to build safely and effectively on soft soils. Introduction to the problem. Soft soils like clay, silt, and peat present a huge problem for construction. They lack the strength and stability to support heavy structures, leading to issues like sinking, shifting, and even structural failure. In many parts of the world, particularly in coastal or river regions, soft soils are the norm. So how do engineers overcome these obstacles to build skyscrapers, bridges, and infrastructure on such tricky ground? Key engineering solutions. Over the years, engineers have developed innovative techniques to transform unstable soils into safe building foundations. Let's take a look at some of the most effective methods. First, we have soil compaction. By using heavy machinery, engineers can compress the soft soil, increasing its density and strength. This process minimizes the soil's ability to shift or settle under the weight of a structure. Next, there's soil stabilization, which involves mixing soft soils with stabilizing agents like lime, cement, or even chemicals. These additives react with the soil to improve its strength and reduce its moisture content, making it more suitable for construction. Another technique is deep foundations, where instead of relying on surface soil, engineers drive piles, long columns made of concrete, steel, or wood, deep into the ground until they reach stable soil or bedrock. This allows the structure to transfer its load to a more secure layer, bypassing the soft soil entirely. Finally, there's geotextiles and geogrids. These synthetic materials are laid into the soil to reinforce it, acting like a net to distribute the weight of the structure more evenly. Case study. One famous example of building on soft soil is the construction of the Millennium Tower in San Francisco. Initially built on deep foundations that didn't fully reach bedrock, the tower began to sink and tilt due to the soft soil underneath. Engineers are now using advanced techniques like underpinning and soil stabilization to fix the problem, demonstrating the importance of understanding soil behavior when designing large structures. Building on soft soils is no easy task, but with innovative engineering solutions, we've turned unstable ground into solid foundations for some of the world's most iconic structures. From deep foundations to soil stabilization, civil engineering continues to push the boundaries of what's possible. Thank you for joining us on Blueprint to Reality. If you enjoyed this episode and want to learn more about how engineering solves real-world problems, don't forget to like, subscribe, and hit that notification bell. Welcome to Blueprint to Reality. Today, we're talking about the challenges engineers face when designing buildings in cold climates. How do ice and snow impact building design, and what solutions do architects and engineers use to keep structures safe and efficient? The weight of snow. One of the biggest concerns in cold climates is the weight of snow. Snow loads can put immense pressure on a building's roof and structure. Engineers must carefully calculate the amount of snow that a roof might have to support, based on local climate data. The steeper the roof, the better it is at shedding snow. That's why you'll often see steep-pitched roofs in areas with heavy snowfall. These designs reduce the risk of snow accumulating and overloading the structure. Ice dams and water damage. Another problem is ice dams. When snow melts on a warm roof and then refreezes at the colder edges, It creates ice dams that can trap water. This trapped water can seep into a building's roof and walls, causing serious damage. Engineers combat this by improving insulation and ventilation in roofs to maintain an even temperature and prevent the formation of ice dams. Proper drainage systems are also key, ensuring that melted snow has a clear path away from the building, preventing both ice buildup and water infiltration. Thermal expansion and contraction. Cold temperatures also lead to the issue of thermal expansion and contraction. Materials like steel and concrete expand in warm weather and contract in the cold. Over time, this constant movement can cause cracks and weaken structures. Engineers account for this by using flexible materials in critical areas, allowing buildings to expand and contract without causing damage. Wind and snow drift. Snow doesn't always fall evenly. Strong winds can cause snow drifts, where snow piles up unevenly on one side of a building. This creates unbalanced loads, which can strain the structure in unexpected ways. Engineers design buildings to handle these uneven forces by reinforcing the most vulnerable areas and incorporating wind barriers to control snow distribution. In regions where ice and snow are common, building design requires careful planning and engineering to prevent damage and ensure safety. From steep roofs to advanced drainage systems, engineers use a variety of techniques to keep buildings strong in the face of winter's challenges. Thanks for tuning in to Blueprint to Reality. If you're interested in more engineering insights, don't forget to subscribe and hit the notification bell for more. Welcome back to Blueprint to Reality. Today, we're discussing an important topic for anyone planning to build a home. Things you need to know before starting your project. Whether it's your dream home or a practical space, these tips can help you avoid common pitfalls and make informed decisions. First and foremost, let's talk about budgeting. Building a house can quickly become expensive if you don't have a clear plan. Make sure you include everything in your budget: construction materials, labor costs, permits, landscaping, and even unexpected expenses. It's also a good idea to set aside an additional 10 to 20% for contingencies, as surprises are common in any construction project. Next, consider the location. The land you choose can significantly impact your design and cost. You'll want to check the zoning regulations and local building codes in the area. These will dictate what type of structures you can build, how close to the property line you can go, and what environmental considerations need to be accounted for. Also, think about the future. Access to schools, shops, and transportation can affect long-term value. Design is crucial, not just for aesthetics, but for functionality. Before jumping into the architectural phase, think about your lifestyle. Do you need a home office? What about a guest room or space for future expansions? Pay attention to the layout and flow, how rooms are connected, natural lighting, and storage solutions. Work closely with your architect or designer to ensure the home meets your present and future needs. Building a home requires a team of professionals: architects, contractors, and engineers. Do your research and hire a licensed, experienced contractor who has a good reputation. Don't rush the process of selecting your team, and be sure to check references and past projects. A well-coordinated team can save you time, money, and headaches down the line. Finally, set realistic expectations for your timeline. Construction projects often take longer than expected due to weather, material delays, or labor shortages. Be patient and flexible with your schedule, but also stay involved and keep communication open with your team to ensure things are moving forward. Building a house is a big undertaking, but with the right preparation, it can be a rewarding experience. Keep these tips in mind to stay on track. If you found this video helpful, don't forget to like, subscribe, and hit the bell icon for more home building and construction tips. Thanks for watching, and see you next time on Blueprint to Reality. Welcome back to Blueprint to Reality, the channel where we turn civil engineering concepts into everyday language. Today, we're comparing two critical structural systems used to resist lateral forces like wind and earthquakes: braced frames and moment-resisting frames. Let's dive into how these systems work and when you should use each one. What is a brace frame? First up, the braced frame system. In this system, diagonal braces are added between columns and beams to form triangular structures that provide lateral stability. These braces create a stiff structure, allowing the building to resist lateral forces like wind and seismic activity. There are different types of braced frames, such as X-bracing and K-bracing, each designed for different needs, but they all work by converting lateral forces into tension and compression within the braces. What is a moment-resisting frame? Now, let's talk about the moment-resisting frame system. Unlike braced frames, moment-resisting frames don't use diagonal braces. Instead, the joints between the columns and beams are specially designed to resist rotation, meaning they carry bending moments as well as vertical loads. This system provides flexibility in design and allows for more open spaces, since you don't need diagonal braces to block off walls or windows. However, it relies heavily on the strength of the beam-column connections to resist lateral forces. So, what makes braced frames a good choice? The biggest advantage is their high stiffness. Braced frames are excellent at resisting lateral forces, making them a common choice in areas prone to earthquakes and high winds. They're also typically more cost-effective because braces are easier and faster to install than reinforced beam column joints. However, one downside is that braced frames can restrict architectural design. The diagonal braces often limit where windows, doors, or open spaces can be placed. Now, let's look at the strengths and weaknesses of moment-resisting frames. These frames offer more design flexibility because there are no diagonal braces. This is ideal for buildings that require large, open spaces or where aesthetics are a priority. Moment-resisting frames also allow for more natural light because you can have larger windows or open facades. However, the construction of these systems is more complex and expensive. The joints between the beams and columns need to be carefully designed and reinforced to handle both vertical and lateral loads. Braced versus moment-resisting frames. When to choose. So, how do you decide which system to use? If you're working on a building where lateral stability is the top concern, like in earthquake-prone regions, a braced frame is often the better choice due to its stiffness and cost-effectiveness. But if your project requires flexible design and large open spaces, like in modern office buildings or high-rises, a moment-resisting frame may be worth the extra investment. In the end, both systems play a crucial role in keeping buildings safe and stable. Your choice depends on the balance between design flexibility and lateral strength. Thanks for watching Blueprint to Reality. Don't forget to like, subscribe, and hit the bell for more engineering insights and solutions. Welcome to Blueprint to Reality. Today, we're tackling a question that seems straight out of a sci-fi movie. Can you really build a house in just 24 hours? It sounds impossible, right? But with advancements in technology, what once seemed like a pipe dream might just be reality. Let's break it down and explore the facts. Traditional construction versus modern technology. Now, when we think about building a house, most of us picture a months-long process of laying foundations, putting up walls, roofing, and installing all the plumbing and electricals. But what if I told you modern technology has completely revolutionized this? We're talking about 3D printing, modular homes, and prefabrication, some of the cutting-edge methods that are making fast builds a possibility. Traditional construction involves a lot of manual labor and material delivery delays, but these modern techniques are changing the game. 3D printed houses. Let's start with one of the most exciting innovations, 3D printed homes. Believe it or not, entire houses are now being printed layer by layer using a large-scale 3D printer. This method eliminates the need for traditional bricks, wood, and steel framing, replacing them with concrete or composite materials. But how fast can it really be? In some cases, companies like Icon and Apis.cor have managed to print the walls of a small house in as little as 24 to 48 hours. That's incredible speed when you think about how long it takes to build walls with traditional methods. However, it's important to note that the 24-hour time frame only applies to the structure itself. You'll still need to install the roof, windows, and finish the interior, which can take additional time. Modular homes. Next up, we have modular homes. Think of these as building blocks that are pre-made in a factory, then shipped to your site and assembled like giant Lego pieces. Because the modules are pre-built, the assembly process can take as little as a single day. Yes, that's right, a house assembled in 24 hours. But again, there's a catch. While the assembly is fast, the modules still have to be manufactured ahead of time, which usually takes weeks. So technically, the house can be put together quickly, but the preparation behind the scenes is what makes it possible. Realistic expectations. So, can you really live in a house that was built in 24 hours?
The short answer is, it depends.
While the structure of a home can be assembled or printed in under a day with these methods, the full completion, adding electrical, plumbing, finishing touches, and inspections, still takes time. These quick builds are great for emergency housing, disaster relief, or those looking for ultra-speedy solutions. But for most of us, the idea of a fully livable, custom home in 24 hours is still just a bit out of reach. That being said, the future is bright. We're closer than ever to rapid construction becoming the new norm, and who knows? In a few years, building your dream home in a single day might be a common reality. If you found this video interesting, don't forget to like, share, and subscribe to Blueprint to Reality, where we break down the biggest ideas in civil engineering and construction. Until next time, stay curious. Thanks for watching. Blueprint to Reality. Today, we're tackling a fascinating question. Can you make a beam stronger by making it hollow? It sounds counterintuitive, but let's dive into the science and debunk this engineering myth. The basics of beam strength. First, let's understand the basics. A beam's strength, or its ability to carry loads, is primarily determined by its material properties and its shape. For beams, strength is often measured by their moment of inertia, which is a geometric property that indicates how the beam will resist bending. Traditionally, solid beams are designed with a specific cross-sectional area to support loads. The more material you have, the stronger the beam should be, right? But what happens if you start removing material and make the beam hollow? The science behind hollow beams. Here's where things get interesting. Hollow beams are often used in engineering and construction for a couple of reasons. 1. Moment of inertia. The moment of inertia, which helps determine the beam's resistance to bending, can actually be increased by making the beam hollow, provided you maintain the right shape. This is because distributing the material further from the center of the beam increases its resistance to bending. A hollow beam with a well-designed cross-section can have a higher moment of inertia compared to a solid beam of the same weight. 2. Material efficiency. By hollowing out a beam, you reduce the amount of material used while maintaining its strength. This not only reduces the weight of the beam, but also the overall cost of materials. The key is to optimize the hollow space and ensure that the beam's shape supports the load effectively. 3. Strength-to-weight ratio. Hollow beams can achieve a better strength-to-weight ratio than solid beams. For instance, I-beams and tubular beams are hollow, but are extremely effective in resisting bending and shear forces. They're designed to be strong and lightweight, making them ideal for applications where reducing weight is crucial. Real-world applications and limitations. Hollow beams are widely used in various applications, such as in bridges, high-rise buildings, and even in aerospace structures. They allow for longer spans and reduce the load on supporting structures. For example, steel and concrete hollow core slabs are common in floor systems because they offer good strength with reduced weight. However, there are limitations. Designing hollow beams requires precise engineering to ensure they can handle the intended loads and stresses. If not designed correctly, hollow beams can be prone to issues like buckling or stress concentrations. Debunking the myth. So, can you make a beam stronger by making it hollow? The answer is yes, but with qualifications. A hollow beam can indeed be stronger in terms of its strength-to-weight ratio and moment of inertia, if designed correctly. The key is in optimizing the design so that the hollow beam performs well under the given loads and stresses. Making a beam hollow doesn't just mean removing material, it's about strategically placing material where it will be most effective in resisting forces. So, while a hollow beam can be stronger in some respects, it requires careful design and engineering to ensure it meets the necessary safety and performance standards. There you have it. Hollow beams can indeed offer impressive strength and efficiency, but it's all about smart design. Thanks for joining us on this myth-busting journey. If you enjoyed this deep dive, don't forget to like, share, and subscribe to Blueprint to Reality for more engineering insights.
See you next time.
Hello everyone and welcome back to our channel. Today, we're diving into an exciting topic in civil and structural engineering, how advanced simulation tools are revolutionizing the field of structural analysis. These tools are not just changing the way we design structures, they're enhancing safety, efficiency, and innovation in ways we couldn't have imagined just a few decades ago. 1. The importance of structural analysis. First, let's briefly discuss why structural analysis is crucial. When engineers design buildings, bridges, or any structure, they must ensure that it can withstand various forces and loads, such as gravity, wind, and seismic activity. Traditional methods of structural analysis often involve simplified calculations and assumptions, which can sometimes lead to suboptimal designs or, worse, structural failures. This is where advanced simulation tools come into play. 2. What are advanced simulation tools? So, what exactly are advanced simulation tools? These tools include software programs that use finite element analysis, computational fluid dynamics, and other numerical methods to create detailed models of structures. By simulating real-world conditions, these tools allow engineers to visualize how a structure will respond to different forces throughout its life cycle. For example, finite element analysis software breaks down a structure into smaller, manageable elements, calculating how each one behaves under various conditions. This level of detail provides insights that traditional methods simply cannot offer. 3. Benefits of advanced simulation. Now, let's talk about the benefits of using these advanced simulation tools in structural analysis. 1. Enhanced accuracy. One of the primary advantages is enhanced accuracy. By taking into account the unique material properties, boundary conditions, and load scenarios, engineers can make better-informed decisions. This leads to designs that are not only safer, but also more efficient in material usage. 2. Cost efficiency. Next is cost efficiency. Although there may be an initial investment in software and training, the long-term savings are significant. With accurate simulations, the need for costly physical prototypes and extensive testing is reduced. Engineers can optimize designs and identify potential issues early in the process, saving both time and money. 3. Improved safety. Moreover, safety is a critical concern in engineering. Advanced simulation tools enable engineers to conduct comprehensive risk assessments and safety evaluations. By simulating extreme conditions, such as earthquakes or heavy winds, engineers can better understand how structures will behave and implement necessary reinforcements or changes before construction begins. 4. Real-world applications. Let's look at some real-world applications. For instance, in the aerospace industry, companies use advanced simulation tools to analyze the structural integrity of aircraft components under various flight conditions. In civil engineering, simulations help design earthquake-resistant buildings in seismic zones, ensuring they can withstand potential disasters. In conclusion, advanced simulation tools are a game-changer in structural analysis. They provide engineers with the ability to create safer, more efficient, and cost-effective designs. As technology continues to evolve, we can expect even more innovative solutions that push the boundaries of what's possible in engineering. Thank you for joining us today. If you found this discussion insightful, please like, share, and subscribe for more content on engineering topics. Until next time, keep innovating and pushing the limits of design. Welcome back to Blueprint to Reality. Today, we're going to break down the key differences between two popular slab systems in building construction: flat slabs and two-way slabs. Both systems have their strengths and weaknesses, but which one is right for your project? Let's find out. First, let's talk about structural design. In a flat slab system, the slab is directly supported by columns, without the use of beams. This allows for a simpler and cleaner ceiling design. However, since there are no beams, flat slabs rely on thicker concrete and larger column heads, or drop panels, to distribute loads effectively. On the other hand, two-way slab systems use beams that connect columns, and the slab rests on these beams. The load is transferred in two directions, both along the length and the width of the slab. The presence of beams means the slab itself can be thinner, but the ceiling design may be less aesthetically flexible due to the beam projections. Next is how each system handles load distribution. In a flat slab, the load from the slab is transferred directly to the columns. Because of this direct load transfer, flat slabs need to be thicker or require the addition of column capitals to prevent punching shear failures, especially in areas with high loads. This can lead to increased material usage. In a two-way slab system, the load is transferred across beams in both directions, which distributes the load more evenly. This leads to a more efficient design for handling heavier loads, especially in multi-story buildings or structures with a grid-like layout. Now, let's talk about design flexibility and space utilization. One of the main advantages of the flat slab is the freedom it offers for open spaces. Without beams, you have more design flexibility for architectural layouts, especially for offices, malls, or parking garages. You can create large, open rooms without the visual or spatial interruption of beams. In contrast, two-way slabs require beams, which can limit interior space design. Beams create drops in ceiling height and may affect the positioning of utilities, lighting, and partitions. However, the added strength of this system can allow for thinner slabs and a potentially lighter structure overall, which is beneficial in smaller-scale projects or residential buildings. Cost and construction time are always important considerations. Flat slabs are generally quicker to construct because of their simpler formwork. The absence of beams means fewer steps during construction, which can reduce labor costs and save time. But remember, the thicker slabs and additional reinforcement may increase the cost of materials. Two-way slabs, on the other hand, involve more formwork and reinforcement due to the inclusion of beams, which can slow down construction and increase labor costs. However, the overall material cost may be lower, especially if the beams allow for thinner slabs. So, when deciding between flat slab and two-way slab systems, it comes down to your project's needs. Flat slabs offer more open space and speed, while two-way slabs give you more strength and cost efficiency in certain designs. Thanks for watching. If you enjoyed this breakdown, hit like and subscribe for more civil engineering insights, only on Blueprint to Reality.
See you next time.
Hello everyone and welcome back to our channel. Today, we're diving into an exciting topic in civil and structural engineering: how advanced simulation tools are revolutionizing the field of structural analysis. These tools are not just changing the way we design structures. They're enhancing safety, efficiency, and innovation in ways we couldn't have imagined just a few decades ago. 1. The importance of structural analysis. First, let's briefly discuss why structural analysis is crucial. When engineers design buildings, bridges, or any structure, they must ensure that it can withstand various forces and loads, such as gravity, wind, and seismic activity. Traditional methods of structural analysis often involve simplified calculations and assumptions, which can sometimes lead to suboptimal designs or, worse, structural failures. This is where advanced simulation tools come into play. 2. What are advanced simulation tools? So, what exactly are advanced simulation tools? These tools include software programs that use finite element analysis, computational fluid dynamics, and other numerical methods to create detailed models of structures. By simulating real-world conditions, these tools allow engineers to visualize how a structure will respond to different forces throughout its life cycle. For example, finite element analysis software breaks down a structure into smaller, manageable elements, calculating how each one behaves under various conditions. This level of detail provides insights that traditional methods simply cannot offer. 3. Benefits of advanced simulation. Now, let's talk about the benefits of using these advanced simulation tools in structural analysis. 1. Enhanced accuracy. One of the primary advantages is enhanced accuracy. By taking into account the unique material properties, boundary conditions, and load scenarios, engineers can make better informed decisions. This leads to designs that are not only safer, but also more efficient in material usage. 2. Cost efficiency. Next is cost efficiency. Although there may be an initial investment in software and training, the long-term savings are significant. With accurate simulations, the need for costly physical prototypes and extensive testing is reduced. Engineers can optimize designs and identify potential issues early in the process, saving both time and money. 3. Improved safety. Moreover, safety is a critical concern in engineering. Advanced simulation tools enable engineers to conduct comprehensive risk assessments and safety evaluations. By simulating extreme conditions, such as earthquakes or heavy winds, engineers can better understand how structures will behave and implement necessary reinforcements or changes before construction begins. 4. Real-world applications. Let's look at some real-world applications. For instance, in the aerospace industry, companies use advanced simulation tools to analyze the structural integrity of aircraft components under various flight conditions. In civil engineering, simulations help design earthquake-resistant buildings in seismic zones, ensuring they can withstand potential disasters. In conclusion, advanced simulation tools are a game-changer in structural analysis. They provide engineers with the ability to create safer, more efficient, and cost-effective designs. As technology continues to evolve, we can expect even more innovative solutions that push the boundaries of what's possible in engineering. Thank you for joining us today. If you found this discussion insightful, please like, share, and subscribe for more content on engineering topics. Until next time, keep innovating and pushing the limits of design. Welcome to Blueprint to Reality. Today, we're exploring an incredible engineering feat: how earthquake-proof buildings can bounce back from destruction. Earthquakes can cause severe damage, but advancements in building technology are helping structures recover and even survive intact. Let's dive into how this is possible. The basics of earthquake-proof design. First, let's understand what makes a building earthquake-proof. Earthquake-resistant buildings are designed to withstand seismic forces through a combination of smart engineering and advanced materials. Key features include flexible foundations, which allow buildings to absorb and dissipate seismic energy. Instead of collapsing, these structures are designed to sway and shift without losing their integrity. They also incorporate dampers, devices that absorb shock and reduce vibrations. Think of them like shock absorbers in a car, but for buildings. Advanced technologies for recovery. But being earthquake-proof is only part of the story. To truly bounce back, buildings must be able to recover from damage and remain functional. Here are some cutting-edge technologies that help buildings recover after an earthquake. 1. Base isolators. These are large, flexible bearings placed between a building's foundation and its superstructure. They allow the building to move independently of the ground motion, reducing the amount of stress transferred to the structure. 2. Self-healing materials. These innovative materials can repair themselves after sustaining damage. For example, self-healing concrete contains special capsules that release healing agents when cracks form, helping to restore the concrete's strength and durability. 3. Post-earthquake reinforcement. Some buildings are equipped with systems that allow for rapid assessment and reinforcement after an earthquake. These systems can detect damage and automatically deploy additional supports or reinforcements to ensure the building remains safe and functional. Real-world applications and examples. Real-world applications of these technologies are already making a difference. In Japan, a country with high seismic activity, many buildings are designed with base isolators and advanced damping systems. The Tokyo Skytree, for example, is equipped with a massive damping system that helps it sway safely during an earthquake. Similarly, buildings in California, a region prone to earthquakes, are being constructed with self-healing materials and other advanced technologies. These innovations not only protect lives but also minimize disruption to businesses and communities after a quake. The future of earthquake resilience. The future of earthquake resilience is promising. Ongoing research is focused on developing even more advanced materials and technologies to enhance building recovery. Innovations like shape memory alloys, which can return to their original shape after deformation, and more effective early warning systems are on the horizon. As we continue to improve earthquake-resistant technologies, we're moving closer to a future where buildings can not only withstand but also quickly bounce back from the impact of earthquakes, making our cities safer and more resilient. So there you have it. Earthquake-proof buildings are not just about surviving the quake, but about bouncing back stronger than ever. Thanks for tuning in. If you found this video insightful, be sure to like, share, and subscribe to Blueprint to Reality for more engineering breakthroughs.
See you next time.
In the world of engineering, Bridges have always symbolized the connection between 2 points, overcoming physical barriers with elegance and precision. But today, engineers are pushing the boundaries even further. Modern bridge designs are redefining what's possible, blending sustainability, innovation, and structural efficiency. 1. A shift toward sustainability. Bridges are no longer just about connecting roads. They're also about connecting people to a sustainable future. Engineers are designing with eco-friendly materials and practices to reduce carbon footprints. For example, we're seeing the rise of bridges constructed from recycled materials like plastic waste, which reduce the environmental impact. The use of modular construction, where sections are built off-site and assembled on-site, not only speeds up the process but also minimizes waste and emissions during construction. 2. Innovation in structural design. Engineers are also experimenting with new shapes and forms. Traditional bridge designs like suspension and arch bridges are still relevant, but now we're seeing incredible geometric innovations. Think of bridges with lightweight, yet incredibly strong, materials such as carbon fiber composites. These materials allow for thinner, sleeker designs without compromising safety or durability. Some futuristic designs include self-healing concrete, a material that can repair cracks on its own, extending the lifespan of bridges while reducing the need for frequent maintenance. This not only saves money, but also increases the safety of the infrastructure. 3. Smart bridges, the future of connectivity. Perhaps the most groundbreaking development is the rise of smart bridges. Imagine a bridge that can monitor its own health in real time. Sensors embedded in the structure can detect stress, strain, temperature, and even potential weaknesses before they become critical. This data is transmitted to engineers who can analyze it and make real-time decisions on maintenance. Smart technology also helps in predicting how a bridge will behave under certain conditions, like heavy traffic or extreme weather. These insights make it possible to ensure the safety and longevity of bridges, all while minimizing disruptions to daily life. 4. Aesthetic and functional synergy. It's not just about functionality. Modern bridge designs are fusing aesthetics with practicality. Many bridges today are works of art, designed to be both functional and beautiful. Think of the Millau Viaduct in France or the Zhangjiajie Glass Bridge in China. These bridges attract tourists and blend harmoniously with their surroundings, showcasing that a bridge can be more than just infrastructure. It can be a landmark. As the world demands more resilient, eco-friendly, and smarter infrastructure, engineers are responding with creative solutions that challenge traditional boundaries. From sustainable materials to smart technology, the bridges of tomorrow are being built today. They don't just connect us physically, they represent the future of engineering innovation. Thanks for watching, and stay tuned for more insights into the ever-evolving world of structural engineering. How do engineers optimize load-bearing structures? Welcome to Blueprint to Reality. Today, we'll explore one of the core concepts of structural engineering, optimizing load-bearing structures. How do engineers ensure buildings stand tall, bridges stretch far, and towers reach for the sky without collapsing under their own weight? Let's dive into the fascinating process behind making structures both strong and efficient. What is load-bearing? First, what exactly does it mean for a structure to be load-bearing? At its most basic, it's any part of a building or a structure that supports weight, or in engineering terms, loads. This includes walls, columns, beams, and floors. These components don't just carry their own weight. They distribute external forces like gravity, wind, earthquakes, and even people walking on a floor. If a load-bearing element fails, the whole structure could be at risk. This is why engineers spend significant time calculating how to manage these loads effectively. The key principles of load optimization. Engineers optimize load-bearing structures through several fundamental principles. 1. Material selection. Different materials have varying strengths. Steel, concrete, wood all have unique properties. Engineers choose materials that balance strength, cost, and durability. For example, steel is strong but expensive, while concrete is more cost-effective and excellent in compression. 2. Efficient shapes. Geometry plays a key role. Triangles and arches are often used because they distribute loads more efficiently than squares or rectangles. That's why you see triangular trusses in roofs and arched bridges. They're strong and require fewer materials. 3. Load distribution. Engineers design structures so that loads are evenly spread across multiple components. Instead of a single beam bearing all the weight, that load is shared across several beams or columns. Think of it as teamwork for materials. No single part bears the entire burden. 4. Redundancy. This means creating alternate load paths. If one part fails, another part can still handle the load. This prevents catastrophic collapses, making structures more resilient in emergencies. Examples of optimized structures. Take the Burj Khalifa, the tallest building in the world. Engineers used a system called the buttressed core, a Y-shaped design that evenly distributes the weight of the tower, reducing the load on any one point. This allows it to soar to 828 meters while still being stable. Or consider suspension bridges like the Golden Gate Bridge. The cables distribute the bridge's load, allowing it to span incredible distances while staying light and flexible. These examples show that optimization isn't just about using strong materials, it's about using them intelligently. In conclusion, optimizing load-bearing structures is a delicate dance between physics, materials, and design. Engineers must balance all these factors to ensure that buildings are both strong and cost-effective. The next time you walk into a skyscraper or drive over a bridge, remember, it's not just a structure, it's a carefully crafted solution designed to bear the loads of our world. Thanks for joining us on Blueprint to Reality. Don't forget to like and subscribe for more engineering insights. Hello everyone and welcome back to our channel. Today we're exploring an exciting topic in structural engineering, innovations in tension and compression structures. These elements are crucial in our designs, influencing everything from bridges to skyscrapers. Let's dive into the latest advancements shaping these foundational concepts. 1. Understanding tension and compression structures. First, let's clarify what we mean by tension and compression structures. Tension structures are built to withstand pulling forces, like cables and fabric structures, such as tents. Compression structures resist pushing forces, with examples including columns and arches. Both types play vital roles in creating stable and efficient designs, and recent technology has enhanced their application. 2. Innovations in tension structures. Now, let's look at innovations in tension structures. 1. High-performance fabrics. New synthetic fibers provide greater strength-to-weight ratios, enabling larger, safer tension structures like tensile roofs. 2. Dynamic tension systems. Innovations in dynamic tension systems allow for automatic adjustments based on environmental changes, improving stability in varying conditions. 3. Innovations in compression structures. Next, we have compression structures. 1. Advanced concrete technologies. Ultra-high-performance concrete, UHPC, offers exceptional compressive strength, allowing for slimmer, more ambitious designs. 2. 3D printing. 3D printing technology enables the creation of complex compression structures that optimize material use and allow for rapid on-site construction. 4. Integrating tension and compression. Combining tension and compression elements is leading to innovative hybrid designs. 1. Cable-stayed bridges. These structures use tension cables to support the bridge deck, while compression towers provide stability, resulting in lightweight, aesthetically pleasing designs. In conclusion, innovations in tension and compression structures are transforming design and construction. From advanced materials to 3D printing, these advancements enhance the efficiency and safety of our built environment. Thank you for joining us today. If you found this discussion insightful, please like, share, and subscribe for more on structural engineering innovations. Let's explore the future of architecture and engineering together. Hey everyone, welcome back to Blueprint to Reality. Today, we're tackling an important topic in civil engineering: reinforced concrete versus pre-stressed concrete. Both are widely used in construction, but what sets them apart? Let's break down the key differences and help you decide which one suits your project better. Let's start with reinforced concrete. A reinforced concrete is made by embedding steel reinforcement bars, or rebar, into concrete to increase its tensile strength. Concrete is naturally strong in compression but weak in tension, and rebar helps compensate for that by resisting the tensile forces that concrete can't handle on its own. This type of concrete is commonly used in residential buildings, bridges, and roads because it's relatively simple and cost-effective to produce. The rebar is positioned before the concrete is poured, and once it cures, the steel works together with the concrete to resist loads. However, cracking can occur if the tensile stress exceeds the steel's capacity. Now, let's move on to pre-stressed concrete. A pre-stressed concrete takes the concept of reinforcement a step further. Before or during construction, steel tendons or cables are pre-tensioned or post-tensioned to put the concrete under compression. Since concrete performs best under compression, this process allows pre-stressed concrete to resist both compression and tension much more effectively than reinforced concrete. A pre-stressed concrete is often used in larger structures, like bridges, parking garages, and high-rise buildings, where minimizing cracks and deflections is crucial. By applying tension to the steel cables, the concrete remains in compression even under heavy loads, reducing the risk of cracking and allowing for longer spans and thinner slabs. So, what are the key performance differences between the two? First, crack resistance. Reinforced concrete can develop cracks under tensile loads, which can lead to structural issues over time if not properly maintained. Pre-stressed concrete, on the other hand, is designed to minimize or even eliminate cracks because of the pre-applied compression forces. Second, load-bearing capacity. Pre-stressed concrete is much stronger and can handle heavier loads and longer spans without sagging or cracking, whereas reinforced concrete is better suited for shorter spans and moderate loads. Finally, deflection. Pre-stressed concrete deflects less under load due to the tension steel, making it ideal for projects where minimizing deflection is critical. Now, let's talk about cost and complexity. A reinforced concrete is simpler and cheaper to produce, making it a go-to option for smaller projects or structures where high loads and long spans aren't as important. It's easy to work with, and the construction process is straightforward. A pre-stressed concrete, on the other hand, is more complex and requires specialized equipment and labor for tensioning the steel cables. This increases both the cost and construction time. However, the benefits of increased strength and reduced cracking make pre-stressed concrete worth the investment for larger, more demanding projects. So, there you have it. Reinforced concrete is great for simpler, smaller structures, while pre-stressed concrete excels in high-load, long-span, and crack-sensitive projects. Thanks for watching. Don't forget to like, share, and subscribe for more civil engineering tips right here on Blueprint to Reality. See you in the next video. Welcome back to Blueprint to Reality, where we turn technical concepts into simple ideas. Today, we're comparing two of the most common structural systems in construction, load-bearing wall systems and frame structures. Let's break down how these systems differ and which one is right for your project. What is a load-bearing wall system? First up, the load-bearing wall system. This is one of the oldest construction methods, used in everything from ancient stone buildings to modern-day homes. In this system, walls carry the load of the building, both vertical loads, like the roof, and lateral forces, like wind or earthquakes. These walls act as the primary support, and as a result, they can't be easily modified without affecting the building's stability. One important thing to remember: load-bearing walls usually limit the size of windows and openings because the walls need to remain strong to support the structure. What is a frame structure? Next, let's talk about frame structures. Unlike load-bearing walls, frame structures use a skeleton made from either steel, reinforced concrete, or wood to support the building. In this system, the frame, columns, and beams bears the load, while the walls are mostly non-structural, serving as partitions or for insulation. This allows for much larger windows, open spaces, and flexibility in design because the walls aren't carrying any weight. Frame structures are commonly used in high-rise buildings and modern constructions where open floor plans are important. Let's go deeper into the load-bearing wall system. What are its strengths and weaknesses? On the plus side, load-bearing walls are often cost-effective for smaller buildings, especially homes, because they don't require as much steel or concrete. They also provide excellent thermal insulation, which can make a building more energy efficient. However, The downside is limited flexibility. Once the walls are in place, it's difficult to modify the layout without compromising the structure. And if you're looking to build taller than a few stories, this system becomes less practical due to the need for thicker, stronger walls. Now for the frame structure system. Why would you choose this? Frame structures offer greater design flexibility. Since the load is carried by the frame, walls can be moved or removed entirely, making it perfect for open-plan spaces. This system also supports taller buildings and allows for larger windows, which is why it's popular in high-rise and commercial structures. But there are downsides too. Frame structures can be more expensive to build due to the materials required, like steel or reinforced concrete. They can also require more specialized labor and take longer to construct. Load-bearing versus frame structures. When to choose. So, when should you choose one over the other? If you're building a low-rise structure, like a residential house or a small commercial building, the load-bearing wall system could be a cost-effective and energy-efficient option. However, if you need design flexibility, large open spaces, or if you're going for a tall building, then frame structures are the way to go. In the end, it's all about your project's needs. Load-bearing wall systems offer simplicity and cost savings, while frame structures provide flexibility and support for larger, more complex designs. Thanks for tuning in to Blueprint to Reality. Don't forget to like, subscribe, and hit the bell for more construction insights. When you think of skyscrapers, you probably picture massive steel and concrete structures piercing the sky. But here's a mind-bending question. Could we actually build a skyscraper out of wood? It sounds like something out of a fairy tale, right? Yet, with modern engineering and cutting-edge materials, timber towers are becoming more than just a possibility. They're a reality. Today, on Blueprint to Reality, we dive into the surprising science behind wooden skyscrapers. Traditional views on wood. For centuries, wood has been a go-to material for construction. It's natural, renewable, and easy to work with. But we've always associated it with small, cozy homes, not towering skyscrapers.
Why?
Because traditional wood structures have limitations. Wood burns, it's not as strong as steel, and it decays over time. So how is it possible to build something as tall and complex as a skyscraper using wood? The answer lies in a new type of wood material known as mass timber. Introducing mass timber. Mass timber is not your average 2x4. It's a revolutionary engineered wood product that involves laminating layers of wood together to create a material that's incredibly strong, durable, and surprisingly fire-resistant. One of the most popular types is cross-laminated timber, or CLT for short. Think of it as wood on steroids. What makes mass timber special is its ability to match, and sometimes even exceed, the strength of concrete and steel. Because of its strength-to-weight ratio, it can support massive loads without crumbling under pressure. Fire safety and durability. Now, you might be wondering, wait a minute, how is wood safe in a skyscraper? Doesn't it burn easily? It's a fair question, but here's where the science gets interesting. Unlike smaller pieces of wood that catch fire quickly, mass timber chars on the outside when exposed to flames, creating a protective layer that slows down the spread of fire. In many cases, mass timber buildings have proven to be just as safe, if not safer, than traditional concrete or steel structures in fire tests. And as for durability, these wooden towers are designed to last just as long as any other modern building, with minimal maintenance required. Environmental impact. One of the biggest benefits of building skyscrapers with wood is the environmental impact. Concrete and steel require a lot of energy to produce, and they release tons of carbon dioxide into the atmosphere. Wood, on the other hand, is a renewable resource that stores carbon throughout its life, making it an eco-friendly option. In fact, if we start using mass timber on a larger scale, it could drastically reduce the carbon footprint of the construction industry. We're talking about a greener future, where towering cities are built from sustainable materials. Examples of timber towers. Still skeptical? Well, let's look at some real-life examples. In Norway, there's the Mjøsternet, the world's tallest timber building standing at 18 stories. And it's not alone. Projects like the Ho-Ho Tower in Vienna and Brock Commons in Vancouver are proving that wooden skyscrapers are not only possible, but are already reshaping city skylines around the world. Architects and engineers are pushing the boundaries, and some are even designing timber buildings that could reach 30 stories or higher. The potential for wooden skyscrapers is only just beginning. So, can you build a skyscraper out of wood? The answer is a resounding yes. With mass timber, we've unlocked a new frontier in construction that's not only strong and safe, but also sustainable. As urban populations grow and environmental concerns rise, timber towers could be a key part of the future. If you're as fascinated by the science of building as we are, don't forget to like, share, and subscribe to Blueprint to Reality for more mind-blowing insights into the world of construction and civil engineering. See you in the next episode. Thanks for watching. Welcome to Blueprint to Reality. Today, we're diving into one of the most fundamental debates in structural engineering: steel frames versus concrete frames. Which is better for your project? Let's break it down. First, what exactly are we comparing? A steel frame consists of vertical columns and horizontal beams made from structural steel. These frames are like the skeleton of a building, holding up the weight of everything else. A concrete frame is made from reinforced concrete combined with steel bars. Like steel frames, these structures also act as the skeleton but with a much heavier composition. Let's start with steel. Why is steel so popular? Steel frames are incredibly strong and lightweight. They have a high strength-to-weight ratio, which means less material can support more weight. Steel also allows for flexibility in design. Architects love steel because it can span large distances, which makes it ideal for projects like skyscrapers or large industrial warehouses. However, steel has some drawbacks. It's susceptible to corrosion, especially in harsh weather conditions. This means maintenance costs can add up over time. And steel loses strength in high temperatures, so in case of fire, special fireproofing treatments are needed. Now, let's talk about concrete frames. Why choose concrete? Concrete is extremely durable and handles compression well, making it a solid choice for low to mid-rise buildings. Concrete has excellent fire resistance, and it's great for projects where fire safety is a priority. However, concrete frames are much heavier than steel. That means the foundation has to support more weight, which can increase construction time and cost. Another issue with concrete is its low tensile strength, which is why it needs reinforcement with steel rebar to prevent cracking. Finally, let's talk about cost and construction speed. Steel is more expensive up front, but it can reduce labor costs due to faster assembly. Concrete, while generally cheaper in raw material, takes longer to build due to curing times. However, labor costs are often lower than steel. So if you're looking for a quick build, steel is often the better choice. But if you're focusing on long-term durability and fire resistance, concrete might be your go-to. So, which is better? It depends on your project's needs. Steel offers speed and flexibility, while concrete gives you durability and fire safety. Thanks for watching Blueprint to Reality. Don't forget to like, subscribe, and hit the notification bell for more engineering insights. Welcome to Blueprint to Reality. Today, we're diving into the fascinating world of bridge engineering, specifically comparing two iconic types of bridges: suspension bridges and cable-stayed bridges. Let's explore what sets them apart. Suspension bridges. Suspension bridges are perhaps the most visually striking of all bridge types. They use cables suspended between towers and hold up the bridge deck with vertical suspenders. This design allows for incredibly long spans, making suspension bridges ideal for crossing wide bodies of water or deep valleys. The key feature of a suspension bridge is its main cables, which are anchored at both ends of the bridge and draped over tall towers. These cables carry the load of the bridge and transfer it to the ground. The main cables support the bridge deck through vertical suspenders, creating a distinctive curve known as the sag. Suspension bridges are celebrated for their ability to cover long distances and their aesthetic appeal. They are particularly effective in environments where the spans need to be very long and where it's challenging to place supports in the water or on the ground. Cable-stayed bridges. Cable-stayed bridges offer a different approach. In these bridges, the deck is supported directly by cables that run from the bridge towers. Unlike suspension bridges, which use a continuous cable, cable-stayed bridges use a series of individual cables attached to the towers in a fan or parallel pattern. The key feature here is that the cables in a cable-stayed bridge are anchored directly to the bridge deck and connect to the towers. This design means that the towers bear a significant portion of the load directly, distributing forces efficiently. The cables are attached to the deck in a pattern that can vary from a fan-like arrangement to a more parallel design. Cable-stayed bridges are known for their efficiency and ease of construction. They can be built with shorter spans compared to suspension bridges and are often preferred for medium to long spans. The design provides a modern and sleek look, making them popular for urban environments and river crossings. Comparing the two. So, what are the main differences between these two bridge types? 1. Span length. Suspension bridges excel in very long spans, often exceeding those of cable-stayed bridges. However, cable-stayed bridges are more efficient for medium to long spans. 2. Construction complexity. Suspension bridges require complex construction techniques and larger amounts of material, especially for the main cables. Cable-stayed bridges, on the other hand, are often simpler and quicker to construct due to their less complex cable system. 3. Aesthetics. Suspension bridges are often chosen for their dramatic appearance and iconic design, while cable-stayed bridges offer a more modern, geometric look. 4. Cost. Due to their construction complexity, suspension bridges can be more expensive to build. Cable-stayed bridges are generally less costly, making them a practical choice for many engineering projects. Both bridge types have their unique advantages and applications, and the choice between them often depends on factors like span length, environmental conditions, and budget. Thanks for joining us on this comparison of suspension and cable-stayed bridges. If you found this video insightful, don't forget to like, comment, and subscribe for more engineering insights. Until next time, keep building dreams with Blueprint to Reality. Welcome back to Blueprint to Reality. Today, we're going to explore a concept that's fundamental to every successful building project: symmetry in structural design. Symmetry isn't just about aesthetics, it's a key factor in making structures more stable, efficient, and cost-effective. Let's dive into why symmetry matters so much in engineering. What is symmetry in structural design? First, let's define what we mean by symmetry in structural design. Symmetry occurs when a structure is balanced and uniform in shape, layout, or load distribution around a central axis or point. This balance can be horizontal, vertical, or even rotational. In structural engineering, symmetry helps distribute loads evenly across the building. A symmetrical structure will have equal forces acting on its foundation, walls, and columns, which means the entire structure can resist stresses more effectively. Whether you're designing a bridge, high-rise, or a residential building, symmetry ensures that the forces, like gravity, wind, or seismic loads, are well-balanced and predictable. Benefits of symmetry in stability. Now, let's talk about stability. Symmetrical structures are more inherently stable than asymmetrical ones because the loads are evenly distributed. This is especially important in areas prone to natural forces like earthquakes or high winds. Take earthquakes, for example. When a symmetrical structure experiences seismic forces, the shaking is evenly spread throughout the building. The structure behaves more predictably, reducing the likelihood of stress concentrations that could lead to damage or collapse. Similarly, in tall buildings, symmetry minimizes the effects of lateral forces from wind or even uneven ground settlement. By maintaining symmetry in both the design and load path, engineers ensure that the building will have better resistance to tilting or buckling under stress. Efficiency and material savings. Symmetry also plays a crucial role in efficiency and material usage. When a structure is symmetrical, loads are more predictable, which allows engineers to optimize the amount of material needed. For example, in symmetrical buildings, columns, beams, and foundations can be designed more uniformly. This not only simplifies the construction process, but also reduces material waste and lowers costs. In contrast, asymmetrical designs may require additional reinforcement in certain areas to handle unpredictable loads, leading to increased material use and higher expenses. Symmetry helps balance structural forces naturally, meaning you don't have to over-design certain parts of the building. This translates to more sustainable construction and a more efficient use of resources. Symmetry in aesthetics and functionality. While symmetry is essential for structural integrity, it also adds to the aesthetic appeal and functionality of a building. Symmetrical buildings often look more balanced and visually pleasing. Beyond aesthetics, symmetry simplifies interior layouts, making it easier to plan spaces, utilities, and circulation paths like hallways and staircases. A symmetrical structure can also make future modifications or extensions more manageable. Since the building is balanced, expanding it or making adjustments won't throw off the load distribution, reducing the need for costly reinforcements or redesigns. To sum it up, symmetry in structural design is about more than just looks. It improves stability, efficiency, and even the aesthetics of your project, while saving time and materials during construction. Thanks for tuning in. Don't forget to like, share, and subscribe for more civil engineering tips and tricks, right here on Blueprint to Reality. See you in the next one. Buildings, bridges, or towers, using the right software can make your life a lot easier. So, let's count down the top 5 software for structural engineers that you should have in your toolkit. Number 5. ETABS. Coming in at number 5 is ETABS, one of the most popular tools for structural analysis and design, especially for buildings. ETABS is fantastic for multi-story buildings and has built-in features to handle everything from simple structures to complex high-rises. It offers advanced analysis capabilities like dynamic analysis and seismic load simulation, making it ideal for earthquake-prone regions. If you're working on commercial or residential buildings, ETABS is a great go-to for accurate and efficient structural modeling. Number 4. SDAD.Pro. Next up, at number 4, is SDAD.Pro. This software is widely used for analyzing and designing all types of structures. Whether it's buildings, bridges, or industrial structures, SDAD.Pro has the versatility to handle complex load combinations and perform advanced finite element analysis. It supports multiple international codes, so whether you're working on projects in the US, Europe, or Asia, SDAD.Pro can adapt to local standards. It's perfect for engineers working on global projects or structures that need detailed load simulations. Number 3. SAP 2000. At number 3, we have SAP 2000, another powerful software for structural analysis and design. SAP 2000 is known for its user-friendly interface and the ability to handle a wide variety of structures, from small residential buildings to large bridges and towers. It excels in 3D structural modeling and is widely used in projects that require seismic and dynamic analysis, such as tall buildings and complex infrastructure projects. With integrated design tools, SAP 2000 is great for optimizing your structural design while ensuring it meets safety standards. Number 2. Tekla Structural Designer. At number 2 is Tekla Structural Designer, an excellent choice for those who want seamless integration between analysis and design. Tekla stands out because it allows you to design both steel and concrete structures within the same platform, saving time and improving collaboration. One of its strongest features is its ability to automate repetitive tasks, making it perfect for large projects where efficiency is key. Plus, it integrates well with Building Information Modeling, BIM, so you can easily coordinate with architects and other professionals. Number 1. AutoCAD Civil 3D. And finally, at number 1, we have AutoCAD Civil 3D, a must-have for any structural engineer working on infrastructure projects. Civil 3D excels in designing roads, highways, and drainage systems, but it's also used for structural design and detailing. It's highly customizable and integrates well with other Autodesk products, making it a versatile tool for both design and documentation. Whether you're designing a new highway or a complex steel structure, AutoCAD Civil 3D is a trusted industry standard. So, there you have it, the top 5 software for structural engineers. From ETABS for buildings to Civil 3D for infrastructure, these tools are essential for modern-day engineering. Thanks for watching Blueprint to Reality. Don't forget to like, subscribe, and hit the notification bell for more insights and tips from the world of engineering. Welcome to Blueprint to Reality. Today, we're unraveling one of the most fundamental questions in civil engineering. Why do buildings stand? Let's dive into the science of structural stability. The concept of structural stability. At its core, the stability of a building is about balance, balancing the forces acting on it, and ensuring the structure can carry its own weight and any external loads. Buildings stand because they are designed to handle a range of forces, like gravity, wind, and even earthquakes. A stable structure means that all these forces are properly managed and redirected into the foundation, allowing the building to remain upright and functional over time. 1. Gravity and dead load. First and foremost, buildings must support their own weight, also known as the dead load. This includes the weight of walls, floors, roofs, and every other permanent part of the structure. The force of gravity pulls everything toward the earth, so the building must be designed to resist this downward force and ensure that it's evenly distributed. The materials used in construction, steel, concrete, wood, are selected based on their strength to support this dead load. Engineers calculate how much weight these materials can safely hold without buckling or collapsing, ensuring the building's foundation and frame are up to the task. 2. Live load. But buildings don't just have to support their own weight. They also need to handle live loads, which include things that change over time, like people, furniture, and equipment. Engineers account for these dynamic forces, ensuring that the building remains stable even when it's filled with occupants or heavy machinery. In areas like offices, schools, and homes, live loads can vary significantly. The design must be flexible enough to accommodate fluctuations, like a crowded event or heavy snow on the roof, without compromising stability. 3. Wind and lateral forces. Next, we have lateral forces, especially from wind. Wind doesn't just blow against the side of a building, it can push and pull on the structure, causing it to sway. Engineers account for wind loads by designing buildings with lateral support systems like braces, shear walls, or moment frames. These elements help the building resist side-to-side forces and prevent excessive swaying. Tall buildings, in particular, are prone to wind forces. Skyscrapers often use a tapered design or add dampers, which absorb and dissipate wind energy, preventing the building from becoming unstable during strong winds. 4. Seismic forces. In earthquake-prone areas, structural stability is even more critical. Seismic loads introduce horizontal and vertical forces, shaking the building's foundation. Engineers use techniques like base isolation, cross-bracing, and shock absorbers to prevent excessive movement and ensure the building can withstand these intense forces. Buildings in earthquake zones are designed to be flexible enough to absorb seismic energy without collapsing. This flexibility allows them to sway safely instead of rigidly snapping under the pressure of an earthquake. 5. Foundations and load transfer. All the forces acting on a building, gravity, live loads, wind, and seismic forces, must be transferred safely into the ground. This is where the foundation plays a crucial role. Foundations are designed to evenly distribute the load across a large area, preventing the structure from sinking or tilting. Deep foundations, like piles driven into the ground, are used for tall or heavy buildings to reach stable soil layers. Shallow foundations, like slabs or footings, work for smaller structures where the soil can support the load at surface level. Conclusion. So, why do buildings stand? It all comes down to managing forces and ensuring stability. Engineers balance the downward pull of gravity with the push of lateral forces like wind and earthquakes, transferring these loads safely into the foundation. With careful design and material selection, buildings stand tall and strong, even in the face of the elements. Thank you for tuning into Blueprint to Reality. If you enjoyed this deep dive into structural stability, be sure to like, comment, and subscribe for more civil engineering insights. Until next time, keep building the future. Welcome to Blueprint to Reality. Today, we're diving into a critical issue in skyscraper engineering. What happens when you build the world's tallest building and forget this one crucial detail? It's not just about reaching new heights. It's about ensuring that every aspect of the design and construction is flawless. Let's find out what could go wrong. The challenge of building tall. Building the world's tallest building is no small feat. Engineers and architects face numerous challenges, from structural integrity to wind resistance, and even the foundation. Every detail must be meticulously planned and executed. But what if something critical is overlooked? One crucial aspect that is often discussed, but sometimes underestimated, is the building's foundation. A skyscraper's foundation is not just about supporting the structure's weight, but also ensuring stability against lateral forces, like wind and seismic activity. If the foundation isn't designed and constructed properly, even the tallest building can face severe problems. The importance of foundation. The foundation of a skyscraper is its backbone. It must handle the immense weight of the building, which can be hundreds of thousands of tons. If the foundation is not deep enough, strong enough, or appropriately anchored, the entire structure is at risk. For example, if a foundation is not deep enough to reach bedrock or a stable layer of soil, the building may experience settlement or tilt. Over time, this settlement can cause cracks in the structure and potentially lead to catastrophic failure. Moreover, foundations must account for lateral forces caused by wind and seismic activity. Without adequate design for these forces, the building might sway excessively or even collapse under extreme conditions. Real-world examples and consequences. There have been instances where foundation issues led to major problems. A notable example is the Leaning Tower of Pisa. While not a skyscraper, it illustrates the dangers of an inadequate foundation. The tower began leaning because its foundation was too shallow and the soil beneath was unstable. For modern skyscrapers, inadequate foundations can lead to similar issues, but on a much larger and more dangerous scale. The Burj Khalifa in Dubai, the world's tallest building, had its foundation meticulously designed and constructed to avoid these issues. However, if a project of that scale had overlooked such a detail, it could have resulted in massive structural failures. The role of engineering and precaution. The key takeaway is that every detail in skyscraper construction matters, but the foundation is particularly critical. Engineers and architects must ensure that the foundation can support the building's weight, withstand lateral forces, and adapt to the ground conditions. Any oversight in this area can have severe consequences. Modern technology and engineering practices help mitigate these risks, but the principles remain the same. Thorough planning, accurate modeling, and rigorous testing are essential to avoid disaster. So, there you have it. Forgetting the foundation could spell disaster for the world's tallest building. Thanks for watching. If you found this insight valuable, don't forget to like, share, and subscribe to Blueprint to Reality for more engineering explorations. See you in the next video.